Good evening. My name is Johanna Koljonen and you are watching Crosstalks, a collaboration between two of Sweden's leading universities, Stockholm University and KTH, the Royal Institute of Technology. Please do join us in discussing today's topics on Twitter, where our handle is Crosstalks TV and our hashtag is Crosstalks. If you've been following science and technology news this year, you've heard some of the world's brightest minds expressing serious concern about the development of artificial intelligence technologies. The rise of AI, they say, poses a grave threat to humanity. Others do dismiss these doomsday scenarios as overreactions and focus instead on the many positive and interesting applications of artificial intelligence. Here to discuss the exciting potential of AI research and to assuage our pop cultural fears about robot overlords are Theo Kanter, Professor of Computer Science at the Department of Computer and System Sciences at Stockholm University, Kristina Nilsson Björkenstam, PhD, Computational Linguistics, Stockholm University, and Kristina Smith, Assistant Professor in Computer Science, KTH, Royal Institute of Technology. Welcome to Crosstalks.
Thank you.
Thank you. We might as well start by addressing this notion of the danger of AI right away. You're all working in fields relating to artificial intelligence in different ways. Do you also believe that artificial intelligence is a threat to humans? Theo.
No, I don't believe so, because human mankind is the ultimate tool maker, and so what we're dealing with is really a refined stone axe, and we only have to consider where we start to surrender our control to AI-inspired technologies, and I think this is in the distant future, where we are blurring the boundary between ourselves and the AI. But that said, if we look at the internet today, when we use services like Spotify, where do we sort of do what technology wants us to do? That is the interesting question.
So you're saying no, but we're manipulated by machines already?
We devise things that change us, yes.
Kristina, what about you?
No, I don't worry about AI. I worry about other things. No, I'm not worried. But I think that Theo has a point about us becoming this sort of systems that cater to our interests and that give us what we want. That might be a problem.
Yeah. What about Christian? Do you agree?
So I don't really see the development of evil robot overlords as such. I don't really see the drive to develop those kinds of systems for one thing. But I do think there are lots of things that should concern us in the development of artificial systems and more advanced technology overall. Technological advances of any kind will have effects on society. It's going to change the labor market, it's going to have effects on the economy and the way we lead our social lives and so on. And I think we have to be aware of what kind of changes there are and sort of drive this sort of development in the direction that we really want it to take.
So what are some of these realistic changes that we think these technologies are about to bring about?
So something which has been mentioned a lot in the media lately is that there's a large portion of jobs that exist today that can probably be automated and be done more efficiently with different kinds of machines and computer software. And the people who are currently doing those jobs, of course, could see this as a threat. And society, of course, has to be aware of these things. We're talking about, for instance, autonomous driving is going to mean that it might not be a realistic future now to educate yourself to become a chauffeur, to drive a taxi or a large truck, because those jobs will not survive in the long term. There are other jobs, such as maybe in a further future, medical diagnostics might be done by artificial intelligence instead, and so on.
Yes, to return to your question about the overlords, I think there is something to be said in addition to what Christian is in important points, is that when you see the use of advisory systems, expert systems like Watson developed by IBM, an
Which is
expert
a sort of
system.
diagnostic system
It's
for
a
doctors.
diagnostic
Yeah.
system, and it recommends answers. And when these are being used by policymakers, then you see a convergence towards types of behavior that can worry us. I would like to remind that, for instance, in the 19th, expert systems were used by brokers to respond to stock exchanges developments, and then this led to well, a downfall of these crises.
I'm realizing now we're talking about almost every kind of technology imaginable. Is there a definition for artificial intelligence?
Yes, it's basically about behavior embodied by machines and software. That is the short definition.
I'm not sure I understand that. Is there a longer definition? That is.
Yes, there are two things. One is that we try to mimic the operation of the mind, which we do not understand, and thus we devised tests like Turing tests in order to compare the human to a machine. On the other hand, there is also another definition. Intelligence is basically operational knowledge used by the military, state, government, and so intelligence is also about information, so mind and information.
Intelligence and so on. And I'm just going to finish this whole overlord track of thought here. We're not necessarily talking about self-aware machines.
We might see them in the distant future, but then again, I think we can mimic this behavior, but we don't understand awareness as yet, as in the human brain projects. We are not there yet, but maybe Kristina has an opinion about how much we understand language.
Well, we don't understand language. We don't really know how we process language. We're still finding it out, and so yeah, I think we have some more work to do.
Let's start with Christian. You work with robots in human environments, human-centered environments, basically. Can you tell us some examples of what this means?
So a human-centric environment is an environment that's built for humans. As an example, a trivial example would be your own home. If you have a robot that helps you in your home, that would be a robot in a human-centered environment. But we're also talking about smaller industries. If you have a small manufacturing industry which has been originally designed for human workers, and you want to replace or sort of expand this by adding robot workers into that, those robots will be working in a human work environment.
With humans?
With humans.
Always.
And that has, of course, lots of requirements on the robots that are not present in a typical, purely automated environment like a modern car factory would be.
So what sort of challenges does this entail?
So one of the things is that robots have problems understanding their environment. If I show something to a robot it has never seen before, of course it has no idea how to pick it up, how to use it, how to work with it. And we still have a lot of work to do in research on how to get a robot to understand something like this bottle of water right here. And how would I pour water into a glass? I can, of course, program a robot to pick up this specific bottle and pour water into this specific glass, but it might not be able to use that knowledge in order to pour gasoline from a gasoline container into a car, even though it's basically the same kind of action, because we cannot yet get robots' artificial intelligence to generalize those kind of things. And in a human environment, we don't want, in your home, you don't want to have only one kind of bottle, which is the government sort of issued bottle, which is the only one you're allowed to have, because that's the one that robots understand, right? You want to design your home yourself. And that's a human-centric environment. So it's made for you and for your needs. And to get the robot to operate in there is a very difficult problem.
How far away are we from robots being able to process categories like that? To look at something and say, this is probably a bottle and therefore?
So processing what it is something where we have seen lots of progress in recent years. You show a photograph of something to a computer program when you use something called convolutional neural networks. It's been branded as deep learning, which is the term used a lot. And you see quite good results, for at least for some categories, at least as good as humans. Shown a picture of a cat and you can tell that this is a cat. It's a completely different thing to see a picture of a bottle and to understand what you can do with it. I can pour water from the bottle, I can pour water into the bottle, I can get in a bar fight and hit you over the head with the bottle. There are lots of different uses of a bottle. And not all of these are obvious just from the class itself.
Yeah. Kristina, one of the most challenging things for machine intelligence to understand and process, I would assume, is human language. And this connects, I mean, if you put robots in human environments, everybody always speaks of care for the elderly. So let's think about that. If my grandmother would have a robot in her home, I think she would need to be able to speak to it with language. This also is quite far away, I'm assuming. And this is your field, right?
Yes.
My understanding is, as a computational linguist, among other things, you're researching how children learn languages in order to create computer models of this process. So what are some of the things you have learned? And also baked into this, I guess, is what you were already implying. We don't know how children learn language.
Yeah, that's true. We don't really know. We don't have the
what are we
definite
learning
answer.
now?
We're learning now. What we're trying to model the child and the parent in a home-like environment with objects, and how the parent and the child interact around language. And I think that even though my project isn't geared towards artificial intelligence, but I think that we learn a lot from this natural interaction between parents and children. We see really interesting sort of coaching strategies that the parents use to get the child to do what they want to do. And we see other types of strategies from the child's perspective on how to figure out what this water bottle is and what you can do with it. And we're looking at them just playing, but there are other scenarios as well that would be interesting. And I think that some of these strategies, if we can sort of use them within artificial intelligence, that would be interesting.
So let's see, what kinds of things are we talking about? What would a strategy for a parent be?
A typical strategy is that the parent wants the child to do something, and then they give the child a message. They say what they want them to do, like pick up the ball. And then they want some sort of confirmation from the child that the child has listened and understood, and hopefully they will do what the parent tells them to do. And if the child doesn't do it, then the parent will just repeat the same message. But the form of the message won't be the same. So there's variation. The parent will repeat the same message, but in different form, until the child actually performs this action. And I think that kind of, if we can trigger that kind of behavior in humans, then that would give very good data to a learning system.
But then part of that is also about things like sightlines. So I'll be looking at the ball in a meaningful manner and saying many, many words. So the child retroactively, once they figure it out, do they retroactively learn many of the words that I've used? They learn to connect it to the ball, basically.
Yes, and children use all these different types of signals, and we can see that the parent uses a lot of multimodal extra information for the child, like eye gaze, and it's really, language learning is a lot about learning to interpret the intention of the other person and to understand what the other person might want me to do. And that kind of building of some sort of,
But is that why machines can't do it? Because one always imagines that part of this is just a vocabulary problem. So if you just gave the child a complete vocabulary, this problem wouldn't exist. But we could give a machine all the words and all the sounds and say, go, talk, understand. But that doesn't work.
There are many problems. So one of the major problems about language is that words have more than one meaning. And if you combine words, then those combined words have more than one meaning. And if you combine a lot of words into a sentence, then you have many, many different interpretations. But for a human, those different interpretations might not even be, they're not, they doesn't make sense. So you just ignore them, and you only have one interpretation. But for somebody learning a language, that's not obvious. And so on the one hand, you have that problem that you have many different possible analyses of one sentence. And also it seems that humans, well, we do some kind of maybe statistical processing based on data that we've heard before, But we also do other types of reasoning, common sense reasoning. We know things about the world. We know things about the experience of being a human. We know that if we pour water, the floor will get wet. We know all of these things, and that we need that to reason about language and to understand language.
Yeah, you definitely like the context, and that is something we see with robots as compared. So there's lots of language processing and dialogue systems done completely on computers that have no body, you just have like a microphone and a speaker. And we do with a robot instead, and we get different results. An example in a study we did in Japan, we were talking about this and that as 2 words. So I have this glass, and over there we have that glass, or those glasses. But geometrically speaking, where is the line, where's the boundary line where a glass stops being this glass and starts becoming that glass? If I tell you to pick up that glass, which glass is that, right?
Yeah, and we can decide. If I say this glass, then we've established that that's this glass, and now that is that glass.
Yes, so we have an agreement, and that can be communicated in what we're looking at, and our body language, and our pose, and our gestures. And there's also a specific situation. If there are 2 glasses, typically the glass closer to me is this, and the one closer to you might be that from my viewpoint. But a pair of glasses closer to me, the further glass is going to be basically closer to me than the closer glass was to you, if this makes any sense.
Yeah.
And then in the one case, the glass which is actually further away becomes this in one context, but it's that in another context. So this and that will then point to completely different glasses just because of our spatial context when we're reasoning about
So
them.
if we could break down these kinds of things into rule sets, which I'm assuming is what we're ultimately do, what's the potential here? What are the most exciting possibilities in language processing? Everybody gets to answer if it's relevant to your fields. Kristina?
Well, to me, it would be really wonderful to be able to use natural language as the interface with machines. I mean, that is just, that would be a very good thing, I think, for lots of people with different abilities. And if you have some kind of disability, then you might need to use this very natural way of expressing ourselves.
We're talking about natural ways of expressing ourselves. In our research, we're actually trying to move even away from language as in spoken or written language and talk about body language. And body language is not only about posture and communicating like I'm dominating or I'm sort of scared, but there's even very specific body language. If I would hand you this glass, for instance, the way that I reach over to someone communicates my intention of when to do it and where to place the glass. And somebody is going to accept that glass. And I don't have to tell you, I'm going to give you this glass approximately 30 centimeters in front of you at a height of 72 centimeters. I don't need to give that information. I can show that just by the motion. If we carry something together, if we're moving house, right, and I help you carry a table, and we carry each part of it, I say, okay, you take that side, I take this side, and we start moving. I don't have to instruct you at every single turn and corner. I can basically just push a bit, or you can see my motion and you can follow it.
I see.
Right?
Yes, I see.
So there's lots of
course,
communication, even in the way we move, the way we push things, the way we pull things, the way we stand.
And
where
in a future where everything is going to be more and more automated, we're going to want our clothes and our house and these kinds of, we're going to want this kind of thing to be communicated.
Yes, because
as
you
well.
don't.
Yeah.
That is under the assumption that we're in such an environment that we wish to discuss things with machines. There could be gestures, of course, as in game environments. There could be other ways to interact with intelligence, of course. But I think there are definitely a lot of situations where natural speech, what our intentions are very important. And but I think there are also other ways to interact with intelligence that we're probably not perceiving as artificial intelligence in the same way.
Yeah, your research involves distributed systems and moving intelligence out on the internet. And already here, I realize I don't quite understand. So I know that you work with a project where you're trying to optimize how people move in traffic systems. How is this related to artificial intelligence?
Yes, basically what you can view it as ambient intelligence. So it means that you interconnect things in a total solution, and we're talking about here tomorrow's traffic, where, for instance, Christian's autonomous vehicles people, but even now everything can be connected. You and I can be connected, and all the participants here in a social network that wish to commute to this session. And we want to do it in an optimal way. We want to use our common resources in traffic. We want to use public transport, our vehicles, and we wish our trip to be as pleasant as possible, so optimize. And we wish also to optimize the resource usage in the system such that the energy footprint is minimal, because we waste resources the way we commute. And so all the pieces in this, our cars, we ourselves, the things in a public transport system have to behave optimally.
Yeah.
And they have to cooperate in order to bring about our journey. And this is a kind of intelligence that adapts to us, our preferences. And this is a very different type of intelligence, ambient intelligence in cooperative systems. So what we do is try to look at how to enable these pieces to be aware of the others and to adjust their behavior.
That's fascinating. And this idea, because of course I immediately thought of like a big traffic mastermind. But that's not it. Again, it's distributing it out.
Yeah, you can compare it to an anthill where all the ants have no clue what they are doing together, but still the result is good.
Joining us now on Skype from Switzerland is Jürgen Schmidhuber, Professor in Artificial Intelligence and Scientific Director at the Swiss AI Lab, IDSIA. Welcome to Crosstalks.
My pleasure.
I have heard that your scientific ambition, since you were a teen, has been to build the optimal scientist through self-improving AI and then retire. How close are you today to this goal, or we as a species to that goal, and what are the biggest challenges remaining?
So this ties actually in to some of the things I just heard from my colleagues in this discussion. We already do have rudimentary artificial scientists. And maybe I should mention that all the stuff that we are doing here in my research group is about learning from scratch to understand the world and then use the understanding of the world to achieve goals. And all the stuff that we are doing here, or most of it, is really based on artificial neural networks, recurrent networks that can process not only images like those mentioned by my colleagues before, but really sequences of images, videos, and then we are talking about agents that interact with the world, babies or scientists or other agents who are trying to conduct experiments in the real world and then see what is the outcome and then learn from that how to predict these outcomes, which can all be done by a so-called recurrent neural network, which over time learns to become a predictor of the future, given the past inputs, the past history of observations and actions. And over time, it learns to become better and better at doing that. And then there's the other guy, the controller, the one that is actually generating the actions that shape the input history. Because if I'm looking here, and not there, then I'm seeing something that is different from what I would see over there, and so on. So that's the way how through our actions we all the time shape our history. Now, the big question for not only the optimal scientist, but also for a little baby is, what should I do next to get some interesting input? And there's this formal theory of curiosity and creativity, which essentially says what you should do next is perform an experiment or an action sequence that leads to more data that has an unknown regularity, something irregular which I didn't know yet. Many of the inputs from the environment are hard to predict. They are noisy, you can't really predict the details. However, many of these inputs also are full of regularities. For example, the sun goes up every day, a little baby moves its fingers like that, and then can create a regular impression, a rhythmic feeling in the fingers. And in the beginning, before the baby knows anything about the world, this is still interesting, this is still novel, then it incorporates that, and the whole thing becomes boring. Now the baby is trying to come up with new action sequences that expand its knowledge about
That's
the world.
wonderful. Does this mean, though, that you have robots? You said you have rudimentary artificial scientists. Does it mean that you have robots in the laboratory that are behaving like babies? Trying things and falling.
Yes, absolutely. Yeah, and they start out from nothing. They start from scratch, and then over time they come up with discoveries of new regularities in the environment that they didn't know yet, and they incorporate them into their little brains made of artificial neurons that are recurrently connected, such that their brains actually become general computers. And the big issue is how to find connection weights, strengths of these connections between these different neurons, such that the baby, or this baby robot that we have, over time learns more and more about how to interact with the world, how to achieve consequences that are useful for the baby, that lead to desirable states, such as not too hot, not too cold, don't bump against an obstacle, which causes pain. So pain is an undecided input.
And the researcher parents don't come in and tell you that you're being bad, which I guess is a factor also. This is very exciting. We have a comment from Theo Kanter.
Yes, I think this is really fascinating and promising research, clearly. My question is, since I work with Internet of Things, and that all this work is, of course, using sensing of the environment in some sense, and how much information from distributed sensor networks could you use and make useful use of in your research? What is sort of the scope of this? How much input can you deal with?
The answer is the scope is in principle unlimited. The nature of the sensors is unlimited. We can deal with speech, we can deal with vision, we can deal with tactile inputs, and we feed it all into the same type of system, which is a big recurrent neural network, which can then learn to take all these different sensor modalities, including those that are not known to man, like, for example, radar sensor inputs and LIDAR sensor inputs and whatever, and then cross-correlate them and figure out how are they related, and then in the end produce actions that lead to desirable goals. And in fact, at least in the pattern recognition domain, which is easier than this action perception cycle, where it's just the goal to recognize patterns such as speech or videos or so, in some of these domains, our neural networks already can achieve human competitive performance, sometimes even superhuman performance. And the big companies, Google and Microsoft and IBM, they are all using our recurrent neural networks now to improve speech recognition, video recognition, image caption generation. One of my colleagues has a while ago mentioned images that are being handled or being analyzed by something called convolutional networks. But on top of that, then sits one of our LSTM recurrent networks that generates out of that a natural language, a string. For example, it says, it looks at an image and then it says, a herd of elephants walking across dry grass in front of a forest. And you look at the image and yes, that's true, that's it, that's what you see on the image. And this is just achieved by putting lots of data, lots of images, which are labeled by some captions, and then from there the recurrent network learns to produce not always perfect, but pretty reasonable captions from many of these images, learning that from scratch.
Professor Schmidhuber, I know you're also very interested in art, culture, creativity. Do you think machines can learn to understand art or to be creative? I'm not sure what that would mean. Do you think this will be possible in the future?
Yes, it's very simple to build that, because that, again, goes back to the previous answer. Suppose you have a system consisting of two modules. One is the controller and the other one is the world model. Both of them learn over time to become better modules, in the sense that the world model better and better predicts the next inputs given the previous history of actions and inputs, and the controller experiences a moment of joy whenever the world model makes progress, in the sense that it can encode the same observation sequence with less computational resources than before, such that at some point before the insight, it needs so many synapses and neurons to encode the observations, and suddenly it sees a regularity which allows it to compress the whole thing such that it needs only so many fewer resources. First so many, then afterwards so many. And the difference between before and after, that's proportional to a little joy signal, an intrinsic reward, a wow effect, an insight. And this is just a real number. I can measure it, and give it to the other guy, the controller, which is trying to maximize it using some standard maximization algorithm, which is trying to maximize these joy signals, the cumulative sum of all these joy signals, and voila, I have an artificial creative artist or scientist who is always motivated to come up with even additional action sequences, experiments, if you will, that lead to additional data that has the property that it's non-trivial, that there is some regularity, some structure in it, which it didn't know, but which it can learn, which its world model can learn, such that afterwards it knows more about the regularities than before. And so for this fleeting moment, then it has another joy signal.
I wonder about the definition of art, but it is a lovely image, the idea of this joyful machine. Christian?
So I would just like to add to this. I mean, I think it's wonderful to have both an artificial artist and an artificial art critic, because then you have sort of completely rationalized away the need for a human at all in the process. But I would also like to add that I see it's completely possible to replace one of these machines or computer programs, if you wish, with a human. So you can have a human who basically tells the machine that, oh, I like this thing and I don't like that, and it can keep generating. So this is also used, for instance, in computer games. So some very popular computer games that you can get as apps to your phones will generate different kinds of difficulty levels that you're playing. And when you generate a level which is too difficult, and you see that the number of users who actually play this level goes down, then they will tweak some numbers and make the level a slight bit easier, and you see that the user numbers go up again, right? And sometimes you see that the level is too easy, and people drop off and they won't play the game. So you have these sort of like automated feedbacks where you sort of generate games which are just easy enough for people to enjoy. And if you, as I do at least, I think games is one art form, then you already have basically automated generators of art that see as a measurement of the number of consumers as a feedback signal to the sort of the critique of the art that you're generating.
Then that does reduce it to popular art form, but I see what you mean,
Yeah,
Theo.
the principle should be the same.
Absolutely, Theo.
Yes, regarding...
Just a moment.
Let me say one thing here quickly. The difference between this very interesting approach that was just outlined and what I said before is, of course, in one case, in the latter case, there is this external environment, the social environment, which provides a feedback, which acts like a teacher. It says, this was good, this was not so good, this was good, this was good. And so from that external signal, the system can learn. In that sense, it is externally guided. And there are lots of algorithms that can be used to implement that guidance into better performance, into better actions. However, when there's no external guidance like that, then another big question is what is interesting in absence of this external guidance? What should my little creative system do when there's no external guy who tells it what to do?
And then the question is, who does it become, in a way? Theo, Kanter.
Yes, I'm connecting it to one of our projects, which is using not neural networks, but sensing to provide care in the home in collaboration. This sensing is then tying in also social networks with significant others, friends and families, and professional care. But then if you would add this functionality to have a personal assistant, if you will, who adds behavior to this local environment, then what would this could then provide a very interesting environment for an elderly who provides. It would provide guidance, and it could be then adapt not only, as in our case, to provide a well-being in terms of detecting that you haven't fallen or something like that, but also guidance how to live your life, take your medicine, and so forth. So this would be then the interactive situation that we're looking at.
Kristina, you told us that you're interested in incorporating humanoid robots into practical research situations when you're researching how children learn language. What are you envisioning there?
Oh, it would be really interesting to bring a baby robot into my home. I would like to see how a baby interacts with siblings, for example, because typically the situation that we use in our research is we try to simplify everything. So there's only one parent and there's one child and nothing else. But that would be interesting to see how other children help a small child to learn, because we know that siblings and other children are very important for language learning. So that would be one thing. And it's also because it's just not ethical to experiment with babies in ways that we might be able to do with robots. So that would be a dream, but it's not something that we're actively pursuing. But there are some very interesting.
But surely there are possibilities. Christian, we must be able to make this happen somehow. To bring a baby robot into a home environment.
So it depends on your definitions of the baby robot. So there, of course, there are robots that are basically the size of a baby, and babies are not very high performance in terms of mechanisms and so on. So we can definitely create a robot that has basically the same performance as a baby, as long as you keep it as a young enough baby. The problem is you want to give it the same behavior. And since we don't really understand exactly all the nature of the behavior of the baby, this is a slightly difficult problem. I mean, you would be studying the robot rather than studying the baby. So that would be a difficult situation. If you're looking into interactions, on the other hand, we can view a baby or a child as sort of like a black box system. We have no idea how it works on the inside, but as long as the actions on the outside are sort of similar, we're happy. If you place a system like that, which might be easier to design, there are different ways to do it. It could be remote controlled by another person, if not nothing else. And you place that with a baby, and then you can see what's the interaction between the real baby and the robot baby, and I think you can have lots of interesting results from that.
Yes, Professor Schmidhuber, did you want to come in?
No, not really.
Oh, very good.
So
If you ask me like that, I always can start going, but I will drift off in another direction, and so.
Very good, Theo. You
should make the next step.
Very good, Theo. You've told us that you think that big data and the internet in itself is a foreign intelligence that we have yet to fully understand. This sounds no. Theo has. This sounds terrifying to me.
Yes, basically because we can do anything in the cloud with algorithms, and we will have through the Internet of Things access to vast amounts of data that in real time monitor any sensor on the planet. That is the type of research that we're doing, and we're pumping all this data into the cloud. And first of all, we have no control of our data, what we surrender to this cloud. And what the result is that we are able to predict, as we heard before, not only with neural networks locally, but also on a global scale, predict and to foresee what we're going to say. So I'm expecting soon services that will predict what I'm going to say the next minute. And then they're already predicting who I should acquaint myself with on LinkedIn. They know my music tastes before I've even told Spotify. And this is going to continue. And it means that we're looking at some ambient intelligence that sort of taps into my mind and extracts what my wishes are. And suddenly I'm confronted by not being in control anymore. And that is the alien part.
Yeah, and certainly I guess even if I mean, this becomes terrifying because it's personal, right? But even if a computer is a learning system, only had access to all of our cultural information as a culture, they could still become better at manipulating us, for instance, for for, I don't know, military or advertising purposes or so on.
Clearly, but this is already happening, and this is what we also wish for. It's sort of the sorcerer's apprentice, and we're alone with his broom, and it's playing with us. And we want service, so we are surrendering our data, because otherwise we won't get service. And we need it because we can't otherwise automate. And this is vital.
That's very right, correct. Let's take some questions from the audience. Who has something on their mind? Please raise your hand. Yes, you can go down to the podium and say your name and your academic affiliation if you have one. And oh, it's very good. Yes. So state your name, please.
So, hi, everybody. My name is Aurélie, and I would like to know why this obsession for performance. I mean, it's like we are all selling our bodies for the science, and I don't understand, because I think we are all talking about like those robots, those implants as something really positive. We are all fascinated, but what about the negative aspect?
Very good.
Where are the limits? I mean.
Thank you. Thank you for your question. So is there an obsession with everything becoming better? And I think a side effect of this is if we create systems that are optimized in every way, doesn't that make being human somehow not quite good enough? Theo?
We discussed this before, and I think we can use it in two ways. And one positive way is saving the planet, because we can have a much smarter way of living. But we can, of course, use it in a bad way. It's like every tool that we have.
So I would say also add a comment in general for any kind of sort of like developments and progress in technology. At many different points in time in history, people have been worried about the next step in technology, but nobody has been willing to let go of the last step, right? So things that are developed 10 years ago, most people in this room would never be willing to let them go, but there are things that might be developed in the next 10 years that you're afraid of, or you think you don't want.
To be fair, not everything we've developed has been to our benefit.
No, I will agree to that. I will agree to that. Not everything. But a lot of the things that have been developed, and there has been a trend in history to sort of put the stop here, right? I think that we have reached optimum right now. We don't have to do all that scary stuff in the future. But we are not willing to let go of whatever happened in the last 10 or 20 years, with a few exceptions, of course. And when you talk to somebody 100 years ago, they're going to be very afraid of the technology which is going to be promised in 10 years in the future from them, and they will be nostalgic about the robot overlords.
Yes, yes, of course. Thank you for your question, Aurélie. And yes, next question, please. State your name and ask your question.
Yeah, hi, I'm Daniel. I'm currently a student at the History of Ideas.
Yes.
And my question is, with the limits of today's binary computer system, does the development of self-aware AI lie within quantum computing? And also, second question, is the problem a hardware or a software problem?
Okay,
Yeah.
let's do that in the remaining few minutes. Let's just develop self-aware AI. I'm not mocking your question, by the way. It's a very good question. Where's the problem with creating a self-aware AI?
Well,
Theo?
we're close to having self-aware systems. If you look at the hardware, IBM just launched their parallel hardware. It's going to be used in UAVs. Unmanned aerial vehicles, and so you can have a swarm of these aircraft performing a task. And this is very interesting. I lost track of the second question. That was about software.
Yes, is it a hardware or a software problem? And is it going to be quantum computing?
And it is basically about a software problem, because we have no clue what is really in our minds. So in order to really capture language, how to handle a bottle, we have to model the world and let it interact also with the world.
I dodged this before. I was trying to not go into this, but let's go into this. Kristina, do you think that being self-aware, it requires language, perhaps, or some some kind of...
Oh,
does it?
oh.
I don't know. That was a big claim.
What a good question. I have a hard, but I'm a linguist. I have a hard time imagining that without language, yes. But I don't know.
Yeah, I think you get a bias because the only self-aware system that we're even starting to get some sort of understanding of is ourselves. I'm not claiming that we do understand ourselves, but it would be even more difficult to imagine, given that we don't have a complete understanding of ourselves, to understand a completely different self-aware system which is nothing like us. So I would just say that even if it's possible to have self-awareness without any language or any of the kind of things that we attribute to ourselves, I think it's very, very difficult to imagine it. And since we don't have any good definitions of what actually is awareness, I mean, there's no consensus on what that is. It's very difficult to answer how do we build it.
Yes. I guess it goes back to some kind of I think, therefore I am level. So
Yes.
it becomes quite banal because then, of course, if it were that easy, we would have solved it already. Do you have an opinion on the quantum computing aspect of the question?
That is certainly on the roadmap, but it's very hard to predict how successful development of these processes will be. That is...
I don't think we're limited, especially if you look into the cloud and internet type of things. I don't think the hardware is the limiting factor for the moment.
Do we have another question from the audience? No, thank you. In that case, I'm gonna take another big step, which I was kind of saying maybe we don't go there. Maybe we will go there. So Ray Kurzweil has predicted that the so-called singularity will happen in 2045. I don't know if you're sighing or nodding, so I'll just finish the question. This, the singularity would be the time when technology is so advanced that we will be able to simulate human intelligence and consciousness so well that a human and machine consciousness could merge. And people are interested in this for the purpose, for instance, to be able to upload their minds and live eternally and so on. But even if we just limit this sort of to being able to simulate human consciousness entirely, do you think this is something that's going to happen and 2045 is potentially in our lifetimes? Is this a realistic projection? Professor Schmidhuber.
So let me first state that this is not the widely accepted idea of a singularity. The whole concept goes back to Stanislav Ulam in the 50s, who in certain discussions with von Neumann came up with the observation that history seems to run faster and faster, technological progress seems to accelerate, and it looks as if within finite time, like an exponential series, this is going to converge. So that's when he came up with this idea of a singularity. And the guy who popularized it was in the 1980s, Werner Vinge, a mathematician who also became a science fiction author. And it was in his science fiction novels that he talked a lot about this technological singularity, a moment in time where technological progress gets faster and faster, in shorter and shorter, and breakthroughs come more quickly and more quickly all the time, such that the intervals between the major steps, they shrink exponentially, which means the whole thing converges in finite time. A particular interpretation of that you put forth there, that's the moment when human and computer minds merge, that is just one little particular interpretation. Which
I accept this, but with the lived experience, it does seem that that technological breakthroughs are accelerating. So doesn't this support the original idea that singularity could in fact happen in our lifetime, no matter how you define it?
Yeah. So I have no doubt that something like that is going to happen within the few decades, a moment in time where humans will not really be able to follow anymore what's going on and will not be the main decision makers anymore. Time will not stop, of course. It will continue as always, physical time. However, there will be some sort of rupture in human history, which has been dominated by humans for at least 40,000 years, maybe longer than that. So the major chapters in the history books of humankind, they accelerate exactly in a pattern that seems indicate that there's a convergence point in the near future. And of course, many people have related that then to the fact that every 10 years we get a factor of 100 in terms of computational power per Swedish krona.
That's excellent. Thank you, Professor. I think this is a wonderful and also slightly terrifying note to end on. Within our lifetime, we are approaching, because of the pace of technological advancement, a rupture in human history. I guess, again, since we're addressing tonight primarily graduate students and people who are picking paths for their research careers, this is a good field to be in right now. I guess that's where we're going to end. Any final words from the studio, Theo?
I think what we're going to develop in light of this discussion is sort of an outer layer of the brain, but it will be artificial, and we can sort of, as a smartphone today, we can just add it to us, and it will be make us more efficient and hook us up to some global intelligence that we can put to our use.
Wonderful.
Yes.
Any other final words, Kristina?
Well, I think we have some more work to do. So
Yeah.
Yeah, we're not quite there yet.
we're not quite there.
Thankfully.
No.
Christian?
No, like you're saying, it might be observed as a natural law, accelerated development, but of course it's carried out by people. So I mean, people who are grad students now will be part of accelerating that process and so on. And I think that can lead to very interesting times, at least in the foreseeable future.
And certainly, I guess, in the academic reality, also the unforeseeable paths of funding will be able to slow it down in very predictable manners. Thank you very much, all. This has been an exciting conversation, but now we are at the end of the show. I will let you all return to your fascinating work. Thank you, Jürgen Schmidhuber, Christian Smith, Kristina Nilsson Björkenstam, and Theo Kanter. Crosstalks will be back in a month with more great minds and intelligent discussions. Be sure to check in at crosstalks.tv for updates on topics and guests. And for now, be safe and be brave.